this video we'll cover the second part of section 8.8. So we talked about improper integrals in the last video with infinite limits. So now we're going to look at the other type of improper integrals that have infinite discontinuities. So the key word here is a discontinuity. All right, so when you're looking at the integral, the limits are going to be constants. They're not going to be infinite sitting on your limits of integration. But what's going to happen is either limit will be a discontinuity of the function, or there will be some constant inside the interval that is a discontinuity. So I'm actually just going to dive right in with example number 1, because the summary here at the top, I think it's a little confusing the way they've written it, because if you see we have A and B here, and then we all of a sudden have a C. I like to approach it a little bit differently, so I'm going to show you that in part 1. Or through my examples. So looking at example 1, if you look at the interval from 0 to 1, and then we're taking the integral of 1 over the cube root of x, you notice that at 0, this integral would have a discontinuity. So therefore, this is an improper integral. Now, we take care of it the same way that we took care of infinite limits by replacing that with a constant a and talking about the limit as a approaches that 0 value. Now, there is something that you do have to take into consideration. Since 0 is like my left-handed limit, then what I'm going to be doing is approaching 0 actually, so that's going to be like my a. So if you look at, let's say, number 2, we have a discontinuity at a, so you can see here that's my left-handed limit. So then as I calculate my limit as I approach a, then I'm going to be approaching a from the right-hand side, so from the positive right-hand side, because I'm not defined, I'm not looking at the left, to the left of A. I'm coming in from the right and approaching A from the right. So we do have one-sided limits here, so A would be approaching from the right if my lower limit was discontinuous, sorry. And then if my upper limit is discontinuous, then I would be approaching from the left. Okay, so that is something to remember there. All right, so this is my lower limit. So when I recalculate this and think of it as a limit, then that's my lower limit, and I would call that a, just like I did with the infinite limits, as a approaches 0, but then I have to approach 0 from the right-hand side. And then that would be the integral from a to 1, and I'm going to go ahead and rewrite 1 over the cubed root of x as x to the negative 1/3 dx. Okay, so now we're going to integrate, and we get x to the positive 2/3 with a coefficient of 3/2, and evaluate that from a to 1. So we're looking at the limit as a approaches 0. So when you evaluate at 1, this is just going to be 3/2 minus, evaluate at a, and you get 3/2 a to the 2/3. And as a approaches 0, that would just be 0. So my answer here is approaching an area of 3/2. Okay, for the second example, we're also looking at 0 here is our discontinuity. So we're going to do the same setup at the beginning. So we have the limit as a approaches 0 from the right side of the integral from a to 2, and then I'm going to rewrite 1 over x cubed as x to the negative 3 dx. When I integrate this one, we are going to get x to the negative 2 with a negative 1/2 constant. And then that would be evaluated from a to 2. Now, when I evaluate at 2, this would be negative 1/2 times 1 over 2 squared, or 1/4. So that would be negative 1/8. And then you would be subtracting the negative 1/2. So that would be actually adding 1/2 of 1 over a squared, and we're looking at the limit as a is approaching 0 from the right. So as a approaches 0 in that sense, this whole limit is approaching infinity, and infinity minus 1/8 is still infinity. Okay, so that improper integral actually does not exist. So therefore, remember, don't forget the words. This is a divergent, or it said that this integral diverges, whereas the one in number 1 was convergent. Okay, let's look at a slightly different problem in example 3. So now we're looking at the integral from 0 to 2 of 1 over x minus 1 to the 4/3. So notice at both 0 and 2, this function is defined. However, at 1, the function is not defined. So if you have a number inside the interval that does not exist, then you're going to have to split this up into two separate integrals. Now, before I start splitting up, we're going to have to approach how we're going to take the integral here, because this is going to involve u substitution. So u here would be x minus 1, so du would just simply be dx. Now, we talked about in the last class, can we do u substitution with improper integrals? And we found out that the answer to that was yes. So you could do u substitution here where I change my limits of integration in terms of u. And if I do that, so I'm not going to split it up yet. If I do that, then 0 minus 1 is going to be negative 1, and then 2 minus 1 is 1, and then this function would become 1 over u to the 4/3 du. Now, this doesn't make our job really any easier because we're now evaluating from negative 1 to 1 for the function of 1 over u to the 4/3. So we're still having an improper integral, but now at u equals 0. Does not exist. So basically all we did was shifted our function over, which that's what that x minus 1 did anyway. It shifted it 1 to the right, so now when I replaced with u, I'm shifting back to the left, so therefore my limits changed. Okay, so I still have that discontinuity, but if you prefer doing with the u, then let's go and try that way. Okay, so we did an example before where we split it up into 2, so we're going to have to split this up. Since we do not exist at 0 for this u substitution, then we're going to split it at 0. So the way we're going to do this is we're going to talk about the integral from negative 1 to 0, since that's my discontinuity, then plus the integral from 0 to 1. All right, so since 0 is my discontinuity, in the first one, that would be my b, and in my second one, that would be my a. So how I'm going to write that is the limit as b approaches 0. Now, since that's my upper limit, I'm going to be approaching that 0 from the left side of my integral from negative 1 to b, and I'm going to rewrite that as u to the negative 4/3 du, plus, in my second integral, I would have the limit as a approaches 0. That would be my lower limit, so I'm going to approach 0 from the right of the integral from a to 1 of u to the negative 4/3 du. Okay, what I want you to do now is I want you to pause the video and go ahead and write the next line. And so pause the video, do it yourself, and then when you come back, I'll have the next line written. Okay, so all I did in the blue line was integrate u to the negative 4/3. So negative 4/3 plus 1 is negative 1/3. Then you multiply with coefficient of negative 3. Okay, so now the next line, again, I'm going to pause. So we're going to evaluate each of those from b to negative 1. Let's go ahead and pause it. Go ahead and solve it all the way out and see if we get the same answer. Okay, here's my next line. So all I did was evaluate at b minus the evaluate at negative 1, then plus and do from 1 to a. So notice you have the negative 3, and so I just brought those negative 3's out in front of the limit. And then also notice that you have u to the negative 1/3, so that's going to be 1 over the cubed root of u. So when I take the cubed root of negative 1 here, that would be negative 1. All right, so hopefully that all makes sense, so make sure you're good. And now let's look at the final answer. So for 1 over the cubed root of b, as b approaches 0 from the left, this would approach negative infinity. And so then you have a negative 3 times negative infinity, so that would be a positive infinity. Then over here you have 1 minus 1 over the cubed root of a, as a approaches 0 from the right, would be infinity, and then times this negative here, and then times another negative, so that would actually be plus infinity. Now, it's important to see all the different signs there, because if you had infinity minus infinity, then that would be indeterminate. But infinity plus infinity is just infinity. So I know we did all of that But it's important to see each of those steps because sometimes on a multiple choice, they want to just see what the setup might look like. So it's important to know each of those individual steps. Okay, we're going to do one more problem with number 4. Okay, now notice with number 4, I have definitely an improper integral with infinity. But if you notice, that's not the only thing that makes this improper, because also at 0, this would be improper because of the square root of 0. This would also be improper at -1, but that's not in our interval, so we don't have to worry about that. So we have 2 pieces here that make this integral improper, and we have to take care of them both. So whereas in number 3, my improper integral was in the middle of the interval, and I had to split that up. This, number 4, we have 2 sides of being improper, so I still do have to split this up. So you need to pick a value between 0 and infinity in order to deal with that, those 2 separate improper integrals. The easiest one here would be at 1. So I would split this up into the integral from 0 to 1 plus the integral from 1 to infinity. Now, before I do that, I want to take care of how to integrate this problem, 1 over the square root of x times x plus 1, because it's a little bit different than what we've seen before. So you might try several different methods here. If you let u be, and don't write this down for just a second, just watch. Like I've said before in the past, part of u substitution is really guess and check. So some of you may try to use u as x plus 1, then du would be dx. And then you might say, okay, I've got the square root of x, so let's see what x would be, and that would be u minus 1. But then you would be left with the square root of u minus 1 times u, and that really doesn't help you out at all. Okay, so that might be your first, intuition is to try to do that, which, as we see, we actually can't do anything there. All right, so now we need to look at it a little bit differently. A lot of times when we have 1 over something, we're going to be either completing the square or doing partial fractions, or in a lot of cases, arctangent, our friend arctangent. So this is actually an arctangent problem. It doesn't look like it at first, but it actually is. So you need to figure out what u is, and another thing that people might do is they might distribute that square root of x. So you get x to the 3/2 plus x to the 1/2, which would be totally fine, but that's all over 1, so that's not going to lead us anywhere either. So what this actually is you want to make u, in this case, be the square root of x, okay? So then du would be 1/2 x to the -1/2 dx, which would then be 1 over 2 times the square root of x dx. Okay, this is a very strange one, different one than we normally see. So see now that we have this 1 over x dx sitting here, okay? So that's going to be equal to, if we take care of this 2, that's going to be equal to 2 du is equal to 1 over the square root of x dx. Okay, so we have that piece taken care of, but then we've got this x plus 1 here. Well, that's where we would take this and figure out what x is in terms of u. So x would be equal to u squared. Okay, so now when we make all our necessary u substitutions, then we're going to equal the integral from 0 to infinity. And actually, when we do u substitution here, if you want to change the limits, u is the square root of x, so the limits are actually going to stay the same, because the square root of 0 is 0, square root of infinity is infinity. All right, so when we make our necessary u substitutions, we're going to have the 2 du, and so I'm going to bring the 2 out front, and then we have the du. That takes care of everything here that's in the red. And then we have 1 over x plus 1, and x, we said, is u squared, and then plus 1. And now you can see that that definitely is arctangent. Okay, so now that we've taken care of this odd integral, now we're going to take care of the improper integral. So as I mentioned at the very beginning of the video, I'm going to have to split this up, and I'm going to split it up from 0 to 1, and then 1 to infinity. Now that 2 out front, I'm just going to leave that all the way out the front, and then when I get my final answer, I'm just going to multiply that by 2. So this is going to be the integral from 0 to 1, and then from 1 to infinity. Now I don't want to write so much, so I'm going to go ahead and pre-plan here. So at 0, that's my lower limit, so that's going to be the limit as a approaches 0 from the left. And then here, this is my b, so that's going to be the limit as b approaches infinity, and you don't necessarily need left or right there. Okay, so I'm going to rewrite this, and we're going to say this is the limit as a approaches 0 from the left, from a to 1, because that's where I'm going to split it off, of 1 over u squared plus 1 du, plus the limit as b approaches infinity from the integral from 1 to b of 1 over u squared plus 1. Okay, so now when we integrate, we're going to just simply have arctangent of u. So we have the limit as a approaches 0 from the left. Now remember, since my limits didn't change, I can keep it in terms of u. So that's going to be the limit of arctangent of u from a to 1, plus the limit as b approaches infinity of arctangent of u from 1 to b. Okay? All right, and so now hopefully we're pretty good with arctangent. So I'm going to go ahead and pause it. You figure out the rest on your own, see if you get the right answer as me. Okay, so the very final answer here is pi. So let's just make sure that you understand how to do all of this. So my 2 just stayed out front, and then the limit as a approaches 0. So arctangent of 1 is pi over 4. Then arctangent of a as a approaches 0 is just 0. Then over here is the limit as b approaches infinity. Arctangent as it approaches infinity, we talked about the graph of arctangent is approaching pi over 2. And then minus the arctangent of 1 is pi over 4. So then we reduce all of that down and we get pi as our final answer. Okay, so that is the second type of improper integrals, and in class we'll do that final example in the notes.